right, so what do you already know about acids and bases? Nick? Other way around for acidic and basic, but otherwise correct, yes. What else do you know? Yes. Yes, so very basic or very acidic substances can be toxic, damaging. We'll also talk about the difference between strength and concentration. Both of those things can play into how potentially harmful an acid or a base could be. What makes an acid or something acidic or basic? Any ideas? Yeah. It's the other way around, but we'll get to that. So, but yeah, it does have to do with charge and movements of electrons. Although technically that definition of acids and bases and involves electrons, I'll mention it today, but it's actually not something that's part of the curriculum for this topic. But it does tie into the next topic, which is the movement of electrons, just not talked about in so much of an acid-base theory at the IB/SL level. But yes, exactly. It has to do with movement of electrons. We're going to have some positive and negative ions dissociating in water, things like that. So what are some examples of acids or bases? Roger, give me one. Okay. Yep. What else? Yeah? Okay. Tomatoes, coffee, yep. Yeah. Baking soda's a base, yep. Any other? Yeah? Yes, ocean water is slightly basic, yep. We'll talk about that. Water can be either an acid or a base, depending on what it's paired with. Yes. Drain cleaner is basic, yes. All right, so that's a good start. Roger, I'm surprised you didn't say nitric acid. Okay. All right, so when we talk about acids and bases, in the usual, there are several definitions of acids and bases. We're going to talk about, briefly touch on two of them and focus on one. But the one that we're going to focus on talks about the transfer of a proton, which is a hydrogen, a positive hydrogen ion, right? It's just a proton in the nucleus. It doesn't have any neutrons. It doesn't have any electrons if it's positively charged. And so a proton getting transferred from one substance to another, the thing that gives up the proton will be the acid, the thing that accepts the proton will be the base. And we'll show you that in a bunch of equations and things. Why do we call them acids and bases, or acids and alkaline substances? Acid means sour. It comes from the Latin for sour. I actually don't know, I don't remember where the term base comes from, but if something is alkaline, or when we talk about the alkali metals, they form basic substances when they react with oxygen or with water. And that word comes from the Arabic, meaning ashes. So if you burn something and then use the ashes to make something like soap, it becomes alkaline. So most soaps, cleaning products are generally alkaline or basic. So the first guy to kind of the first guy who was published and widely recognized for having a theory about defining what is an acid, did it in terms of hydrogen, things that increase the concentration of hydrogen ions, of protons, or the more accurate way of talking about protons in a solution of water is of the hydronium ions, which is H3O+, when dissolved in water. So he was exclusively looking at things dissolved in water and saying that anything that is acidic is something that's going to increase the proton concentration in the water. Anything that is basic is going to decrease the proton concentration, basically. increase the hydroxide concentration in water. So this guy, Arrhenius, he's when we talk about Arrhenius acids and Arrhenius bases, we're talking about reactions that happen in water where a proton is transferred from one substance to the water molecule, making a H3O plus ion. Okay. So anything that's an acid, acids would be things like hydrochloric acid, nitric acid, etc. Bases would be things that produce hydroxide ions or contain hydroxide ions. So sodium hydroxide, calcium hydroxide, things like that. That was the Arrhenius definition of acids and bases. And now you don't need to worry about this definition anymore. Just the history of it, because then Bronsted and Lowry came up with a definition that expands it a little bit more. It doesn't have to be in a reaction with water, although most of the time we do talk about it in reactions with water. But the Bronsted-Lowry is a little bit of a bigger definition of acids and bases, and it basically says the acid is a proton donor and the base is a proton acceptor. So the acid gives up the H+, the base accepts the H+. So for example, if we put hydrochloric acid, HCl, and mix it with water, the hydrochloric acid is going to act as an acid. The water is going to act as a base. The HCl is going to donate an H+ to the water. So we will end up with our hydronium ion, H3O+, and Cl-. So we'd have chloride ions and hydronium ions. So the thing that gave up the proton is the acid. The thing that took in the proton is the base. Okay. So in this reaction, in our reactant side, the HCl is the acid, the H2O is the base. And this slide is just another way of showing it with the electrons, basically a Lewis-Dot structure of it. Yeah. Ooh, yes, we're going to talk about equilibrium. Yep, for sure. Yep. It does not have an electron. It can't be H+. Remember, hydrogen has one proton? So H+ has 0 electrons. It's just a proton. Yeah. So you can think about it as H+, or you can think about it as a proton. But when it reacts with water, it becomes H3O+. That H+ joins up, hooks up with the water molecule to make the hydronium ion. Okay, another example, though, here is ammonia, NH3, commonly used in cleaning solutions. That is going to accept a proton from a water molecule, making the ammonia the base in this context, and water the acid that is giving up the proton. That's going to give us the ammonium ion, NH4+, and the hydroxide ion. Yes? Yes. Well, presumably this is happening in a solution of water, that you don't have 100%. It's not necessarily a 1-to-1 ammonia to water ratio, but and you wouldn't be able to separate it without doing some kind of electrolysis like we did with the copper and the water. You can't just pour off the H3O+ or the OH- and keep the NH4+. And this is just, again, a Lewis structure. And yeah, all of these, when we write these reactions of an acid or a base with water, you'll notice the double direction arrows, which tells us, like Nick was pointing out, that this is a reversible reaction and there's going to be an equilibrium here. So when we talk, this is, I tried to put the study guide pages up on here as well. When we talk about acids and bases reacting, one of the things that tends to be a little bit tough to get into your head is this idea of conjugate acid-base pairs, so a conjugate acid and a conjugate base. So if we go back to this ammonia reacting with water, the ammonia accepts the proton from the water. But if we go backwards, if we do the reverse reaction, because this is a reversible reaction, then what's going to happen is the NH4 plus, the ammonium ion, is going to act as the acid and give a proton back to the hydroxide to make water. Okay? So if we think about the reverse reaction, then our ammonium becomes the acid and the hydroxide becomes the base. So in the original reactants, the ammonia was the base and the water was the acid. Okay? So when we talk about these when we talk about reactants and products in a reaction with acids or bases, we talk about these conjugate pairs. So whatever the substance is that starts off as a base, when it accepts that proton, it becomes the conjugate acid. So we tend to talk about things in terms of, just like in any equilibrium reaction, we talk about this as if these are the reactants and these are the products. So we say this is the base and this is the conjugate acid of that base. And then in this reaction, water is acting as an acid. It's giving up that H plus. But when it's in hydroxide form, in the reverse reaction, it's acting as a base, right? So the hydroxide ion is the conjugate base of water acting as an acid. No. Well, yes, we'll get to that. The strength generally is inverse. So if you have a very strong base, the conjugate acid tends to be a very weak acid, and vice versa. Yeah. But we'll talk more about strength later. We can do the same thing with the other reaction with our hydrochloric acid and water, where water is acting as a base. In this case, hydrochloric acid starts out as the acid. The conjugate base of that is the chloride ion in the products. Because this, if we're going in the other direction, would act as a base and accept a proton to make HCl. Water in this reaction, in the initial reactants, is acting as a base. So our hydronium ion becomes our acid, our conjugate acid. So the difference between an acid and its conjugate base, or a base and its conjugate acid, is a proton. Okay? So you're just looking at the thing that's exactly the same, except it differs by one proton. So HCl versus Cl minus, H2O versus H3O plus, the difference between them is a proton. Whether it's which direction the reaction is moving in, whether the proton is being lost or gained. All right, so as Devin asked earlier, and as you might have noticed with just those two examples of reactions with water, water can actually go both ways. All right? Water gets to be an acid when it's reacting with a base, and it gets to be a base when it's reacting with an acid. This is called an amphiprotic. It makes water an amphiprotic substance or an amphiprotic species. Amphi, like amphibian, can be both in the water and on land. Amphiprotic means it can give a proton or it can receive a proton, depending on the context. And this is only a thing in the Bronsted-Lowry acid-base theory. It's not really a thing in the Arrhenius theory or in the Lewis theory, but this is Bronsted-Lowry is the theory that we focus on in this class, so in this unit. So you need to know that word, amphiprotic. So the example they give here, so water obviously is amphiprotic in that we can have, let's do this. We can have water, sorry, it's a terrible equilibrium sign. Water can gain a proton to become hydronium, but it can also lose a proton to become hydroxide. So that's what makes it amphiprotic. The same thing is true with a number of substances, and we'll look at this later when we talk about polyprotic acids. But for example, the hydrogen carbonate ion, or bicarbonate. And this is actually a really important reaction because it relates to the reactions that happen in the ocean and relate to ocean acidification and the carbon cycle. But we're not going to talk about that here. Yes? Ah, yes. It's the ide is generally used for a lot of negative ions. It doesn't have to be in an acid-base relationship, although, you know, if we get into the Lewis acid theory, which has to do with electron transfer, then it is kind of like that. And hydronium is like ammonium and things like that, the positive. That tends to be the positive charged ions. So it's not necessarily restricted to acids and bases, but yeah, that's the ide will be negative, the onium will be positive generally. Okay, so hydrogen carbonate can go both ways as well. We can give it a proton. It can lose a proton to become the carbonate ion. It can gain a proton to become carbonic acid. So, and again, these things are always in equilibrium with each other. No. You need to be able to look at that hydrogen carbonate, that bicarbonate ion, and realize that it could both gain a proton and lose a proton. But it's not that, you know, like that specific one isn't necessarily going to be tested. And water reacting with other acids, for example, this is acetic acid, which is the acid in vinegar, also known in the IB world as ethanoic acid. That's the IUPAC name for it. So again, water can react with this to be a base, to accept a proton and become the hydronium ion. But it can also react with an amine compound to create an amino acid and hydroxide ion. So it can act either as a base or an acid, making it amphiprotic. So knowing that water is amphiprotic is super important. That's something you should just know. You should have that memorized. But just understanding the concept of amphiprotic may come in handy. They point out in the study guide, Dr. Jones or Mr. Jones, the guy who does the study guides, that there are two different words here that are commonly confused, amphiprotic and amphoteric. So the amphiprotic is relating to proton movement, so just focused on the Bronsted-Lowry basis. Amphoteric is a bigger definition that is talking about things that can act like an acid or a base in other definitions of acids and bases. But you don't have to worry about it. It's just that if you see that word, amphoteric, it means pretty much the same thing as amphiprotic. And so that you should, like on the exam, only see the term amphiprotic used. All right, so I'm going to post these slides, so you'll have this. We're going to talk about a few common acids. These are not, with a couple of exceptions found in the data booklet, so these are things that you should probably need to memorize. It's kind of like memorizing the common ions, the polyatomic ions. These are basically the polyatomic ions. Many of them are the polyatomic ions that you need to know with some hydrogens attached. So HCl, hydrochloric acid. There's also HF, hydrofluoric acid, HBr, hydrobromic acid, HI, hydroiodic acid. Those are all acids as well. We've got our nitric acid, HNO3. our sulfuric acid. Ethanoic acid, also known here in America as acetic acid, is an organic acid. That's what's in vinegar. And we'll talk a little bit more about this structure when we breeze through topic 10. Carbonic acid is the carbonate ion with some hydrogens. Phosphoric acid is the phosphate ion with some hydrogens. Benzoic acid is, we'll talk about benzene more when we get into topic 10. H3PO4. And the other thing to note on this slide is that each of these, well, not each of these, but these have different numbers of hydrogens. And something that has multiple hydrogens in the context of all of those hydrogens being able to be lost as an acid is polyprotic. So protic for proton. So if something is monoprotic, like HCl or HNO3, that means it only has one proton that it can lose. It only has one hydrogen that can be lost as a proton as an acid. You can also have diprotic substances like H2SO4. Each of those hydrogens can be lost as a proton to serve as an acid. So I could take my H2SO4, that could become HSO4, which could then lose another proton to become SO4 2 minus, and this is HSO4 minus, sorry. So that there's two steps to the acidity of our sulfuric acid. And we'll talk a little bit more about this when we get into calculating pH and stuff, which will be early next week. But understanding that H3PO4 phosphoric acid has 3 hydrogens that it can get rid of. But not all hydrogens are able to be released as protons in a solution, turning that substance into an acid. So for example, our ethanoic acid, or, sorry, this is actually not ethanoic acid, this is methanoic acid. Let me just fix that. Oh, this should be. No, it is ethanoic acid. Why is it? Why am I not? Oh, no, I've got that. That's right. Never mind. Sorry. It's been a while getting this. Need 2 carbons, though. And this is different. I just completely wrote this differently last year, or incorrectly. So this is our ethanoic acid. It's got this CH3 group. It's got the carbon double bonded to an oxygen, and then with a hydroxide. So that takes care of our 4 bonds around the carbon, filling up that Lewis dot structure. We've got this oxygen hanging out here, and then we've got this hydroxide. This can actually lose this proton. This hydrogen can easily get lost as a proton. So that's what makes this acidic, is the loss of that particular hydrogen. Because it's bonded to the oxygen, it's a very polar bond. It's very easy to lose this proton. There are other hydrogens here. There are 3 other hydrogens but they're attached to carbons. That bond is a stronger bond. All right, it's not going to, it's not polar. And so these hydrogens are not going to go off and become protons. The carbon doesn't want to be negative the way that oxygen wants to be negative. So this is only a monoprotic acid. Even though it's got 3 other hydrogens, those hydrogens are not going to act in that way. It's only got one that it's going to lose as a proton, the only one that's going to be released in solution. this is not part of the curriculum for this topic, but I just wanted to point out that here we have connection to biochemistry. And if it was a different year and we were doing the options, we might have covered more biochemistry. But think about the things that you think about when you talked about things in bio: amino acids, nucleic acids, all those kinds of things, fatty acids. I didn't include that on here. So an amino acid is acidic because it's got that OH, and that H is going to go bloop when it is in solution. So that's why this is called an amino acid. Nucleic acids, here's a phosphoric acid, which is not an organic molecule, but you can see the similarity between that and the phosphate group in DNA or RNA. And it still has this one OH where the hydrogen can go off and be a proton. So that's why DNA and RNA are made up of deoxyribonucleic acids. The nucleic acids have that phosphate group that has the hydrogen that it can be lost. Okay, some common bases. The oxides and hydroxides are the main ones, okay? They are the metal oxides and metal hydroxides, especially group 1 and group 2. So sodium hydroxide is a very, very commonly used base. Calcium hydroxide, we can make hydroxides with really any metal, but we often see those with groups 1 and group 2. The oxides is going to be basically, this is what forms when the metal rusts, when it reacts with oxygen in the air. And so calcium, or any of the group 1 or group 2 metals can form oxides, but also the transition metals will commonly form oxides as well. And then ammonia, you need to know that ammonia, NH3, is a base. And in this table is also ethanamine, which is also a base because it's got this NH2 group on there. Basically, if you see something with a nitrogen hanging out on the outside, probably a base, or at least that part of it is a base. That's the thing with amino acids, is they kind of have a base side and an acid side. Yeah? Oh, yeah. Gotcha. Okay. Well, I think most of these, I'll go ahead and post, well, actually, it's already up in Classroom. The answer key to the study guide is already in Classroom. So you can fill in from there. I mean, some of the ones in the study guide, you can figure out, like potassium hydroxide is going to be just like sodium hydroxide, just with a K instead of the Na, right? No. Yeah. So some things are in there, but not all of them. Just like the common ion chart is not in the data booklet, right? So, yeah. Oh, yeah. No. Nope. Not include. Yeah, the not part is the key, right? Yeah. Gotcha. So generally, metal oxides, metal hydroxides, ammonia, and then again, we'll talk about amines a little bit when we get into organic. And I will post these slides also. And like I said, the answer key for the study guide is already up. So thinking about biochemistry, when we talk about the structure of DNA, we talk about how it has these nitrogenous bases. And nobody tells you what a nitrogenous base is. They just make you memorize that thymine, cytosine, adenine, and guanine, and they leave it at that. So the nitrogenous obviously means that it has nitrogen. And that's also why it's basic, because in most cases, you're going to have nitrogens here that have a lone pair of electrons just hanging out. And according to the Lewis theory of acids and bases, anything that can donate electrons is a Lewis base, and anything that can accept electrons is a Lewis acid. So Lewis acids and bases encompasses the Bronsted-Lowry, but goes beyond it to things that don't involve proton transfer, but just involve electron transfer. That's all you need to know about it at this point. You don't even technically need to know about the Lewis theory, but that's basically why these are called bases, because they have that nitrogen. What? Generally, when we talk about organic bases, it's usually the presence of a nitrogen, because often the nitrogen is going to bond in a substance in such a way that it has a free lone pair. So, yeah, not exclusively though. Oxygen can act that way too. Other anion or other nonmetals, electronegative nonmetals. Okay, so basically we've just covered some basic types and names of acids and bases. We've talked about acids are things that donate protons. Bases are things that accept protons. We have conjugate acids, acid and conjugate base pairs, along with bases with a conjugate acid. So that's kind of the first chunk of information here. I'm going to go ahead, since we have time, and get started with the next chunk. So this starts on page 7 in your study guide. So this is talking about properties, generally, of acids and bases. And this first slide sort of talks about, general properties that we think of. Like, something tastes sour, it's generally acidic, right? So citric acid from fruits, carbonic acid from soda, things like that, has that sour taste. Yes? No. Think about overcooked broccoli. That's not really sour. Yeah. Bitter chocolate that's not sweetened, that's not really a sour taste. Yeah. Yes. But there's a lot of complexity to coffee and tea. It's not. There are a lot of different substances that can give you those tastes, but generally speaking, these are kind of general things. So acids taste sour. We'll talk about indicators briefly, but not today. But litmus is a common indicator, and acids turn it red. Acids react with metals to produce hydrogen gas. It's a very common lab procedure, and it's a way of making hydrogen. And they also react with carbonates and release CO2. And that, again, is part of the whole ocean acidification carbon cycle issue. But it's also the reason that vinegar and baking soda react to make sort of a volcano. It's not exactly a neutralization reaction, but it's a slightly different reaction with the carbonates. Bases, so things like fruits, a lot of the things we eat and drink are acidic. Bases tend to have a bitter taste. They turn litmus blue, and they tend to be kind of slippery to the touch. So think about what soap feels like, and things that feel like that tend to be basic. They do not have the same reaction with metals. Okay, so that's something to remember specifically for acids. So those reactions with the reactive metals, particularly, again, the more reactive metals that are kind of on that side of the periodic table or towards the top are going to react pretty strongly with acids. So there's an example here of hydrochloric acid reacting with magnesium to produce magnesium chloride and hydrogen gas. The magnesium chloride is an ionic compound that we call a salt. Okay? So sodium chloride obviously is the salt that we all think of as salt, the table salt, but any ionic compound like that we can call salt. So the products of any reaction between an acid and a metal are going to be a salt plus some kind of gas, generally hydrogen, but it could also be carbon dioxide and also water. So the example here with the carbonate reaction, so hydrochloric acid reacting with calcium carbonate is going to give us that salt, that calcium chloride salt. It's also going to give us hydrogen carbonate, and that is then going to, the hydrogen carbonate is going to then produce H2O and CO2. Yeah. Yes, copper nitrate is a salt, yes. So Roger spent a lot of time reacting metal with nitric acid, and what he got out was that beautiful blue solution that was copper nitrate, mostly. And that would be the salt version. But the gas that was created in there was a combination of gases, including the nitrous oxide that we, or nitric oxide that we were very careful to keep in the hood. So you can do things like capture the gas that's evolved and do stoichiometry with this. This is the kind of thing that Hannah, we would use those syringes and tubes for, to capture the gas brought off by a chemical reaction. That's why we have those big syringes that you were using, was actually to collect the gas. But you can, collect it in a test tube upside down, kind of like we did with the butane lab. So these are very common reactions. Being able to look at the metal and the acid and predict the products, and then balance those equations and use them for stoichiometry, that's a very common paper 2 thing to have to do. And then when acids react with bases, we call that a neutralization reaction. So typically, that's going to produce, whether it's these examples are giving metal oxides reacting with an acid or metal hydroxides reacting with an acid. So like sodium hydroxide and hydrochloric acid, that's sort of the classic neutralization reaction. The products here are going to be a salt, again, and then water, because we're going to have the H from the acid and the OH, or the O, combining with water in the solution to make hydroxide. So, for example, got a couple of different, several different reactions on here. I forget which ones are on your study guide, but you can hopefully see the pattern. So, for example, copper oxide is a base. If we react it with sulfuric acid, we're going to take these are going to be double replacement reactions. And that helps you, knowing that helps you predict the products. So if we have, our copper is going to get together with the sulfate to make copper sulfate, and our hydrogen is going to get together with the oxygen to make water. And you can see the same kind of thing here. If we have a hydroxide, that part is also going to react with the hydrogen, and this should be an O3, not a C3. And the sodium is going to pair up with the nitrate. So this is another thing that you might be asked to do. You might be given an acid and a base and asked what the products are going to be. And it might give you a series of products that might be, the wrong products, but it's going to be the salt, it's going to be the metal with the acid anion and water. Those are going to be the products of those reactions always. Okay? So again, this is just another way of showing it, that our acid and our base makes salt and water. If you look at the base and the acid, the OH and the H come together to make water. The other parts come together to make the salt. So it's just another way of looking at it. So that's a neutralization reaction, which is different from when it reacts with just the plain metal, right? That was producing hydrogen. That was producing the salt and hydrogen gas. This is producing the salt with water. We played with some Alka-Seltzer a while back. You may or may not have taken some for medicinal purposes or some Tums when you've got too much stomach acid, if you have indigestion or heartburn. Basically, these are mostly metal carbonates or hydrogen carbonates. And they will react, and sometimes metal hydroxides, they'll react in a neutralization reaction to kind of calm down the acidity of your stomach and your esophagus. All right, and we will continue tomorrow, or Monday, sorry, not tomorrow, definitely not tomorrow. Everybody have a great weekend. Enjoy the goats.